Okay, welcome to lecture here. Excuse me. All right, so we should be picking up where we left off in chapter 13, talking about equilibrium. And again, here, if we would just do our little roll thing just in the chat box there, go ahead and type you're here, and then we'll get started. Okay, so again, we started talking about chapter 13, which is equilibrium. And we talked about the equilibrium sort of condition. Remember that when we do talk about equilibrium, and what we mean by equilibrium again is that we have a reversible reaction. So we have a forward direction. We also have a reverse direction in terms of the reaction. And let's let some people in. Hang on a sec. There we go. All right. So we have a reverse direction and a forward direction. And what it means when it reaches chemical equilibrium is the rate of each of those things will equal each other. So just as quickly as it goes, in the forward direction, it will just as quickly kind of come back in the opposite direction, in the reverse direction. And that's, again, essentially what it means when it reaches equilibrium. Again, doesn't mean, like we talked about last time, that you have the same amount on each side or anything like that. But because the rate of the forward reaction is the same as the rate of the reverse reaction, essentially, as we talked about, everybody will lock themselves in place in terms of, their concentrations at that point, maybe even their pressures at that point if we're dealing with some type of gases. So when a system is at equilibrium, there's a way that we can sort of express it, and that's through the equilibrium constant, which is capital K. And that is essentially the concentration of the products divided by the concentration of the reactants. And we do use the coefficients in the balanced equation as sort of the exponents. So if we had a coefficient in front of something, we would, like a 2, we would take the concentration and square it. Pretty much everything will end up in the equilibrium expression, really, except for two major things. And the two things that we talked about in terms of the equilibrium expression that we do not include, that is things that are solids and things that are pure liquids. So things with the S little symbol next to them in the equation and things with the L symbol. They both pretty much remain constant throughout sort of the reaction, if you will. They really can't participate all that much. So as we talked about, a solid sitting in a beaker really won't participate in the reaction unless you dissolve it. And then obviously at that point, it's no longer a solid. So it would participate because it became maybe an aqueous ion or something of that nature. So that really does leave us pretty much two things that go into the equilibrium expression. That's going to be your gases, and that's going to be your aqueous ions. And really, if you think about it, those are the two states, if you will, where things are really sort of moving around, able to interact well with each other. Obviously, gases are flying around, so they're able to interact pretty good with each other. And if you're in an aqueous environment, you probably have ions floating around in that aqueous environment, and that's going to allow them to basically react with one another. We saw a couple of different types of equilibrium constants to begin our journey here with K. As I mentioned last time, pretty much this class is brought to you by the letter K. So we started with Kc, which is our basically equilibrium constant for concentrations. So we would take the concentration of products over reactants. Now, we also saw that there could be some equilibrium there that's involving gases. So obviously with gases, we obviously will usually see pressure associated with that. So you can write what is referred to as a Kp value, the P standing for pressure there, where we do pretty much the same thing, except instead of concentrations like molarities, we do something like atmospheres. So we take the partial pressure of the products divided by the partial pressures of the reactants. Even with the pressure aspect of it, we do still use the coefficients as the exponents. So we still want to do that when we go through the calculation and everything like that. Numerically speaking, Kp and Kc will not equal the same numerical value, but they will tell you pretty much kind of the same information about the reaction. And that's also something else that we talked about. K is really just a number. We don't usually use any type of units associated with it. But what the number does tell us is when we do reach that equilibrium point where the rate of the forward reaction equals the rate of the reverse reaction, at that point, we can expect either mainly products to be there, or we may expect mainly reactants to be there. And because it's products over reactants, if we have a large value for K, what that essentially means is we would expect mainly products to be there. And vice versa, if we had a small value of K, we would expect mainly reactants to be present at that point. Again, just mathematically speaking, if we take our products on top divided by our reactants on the bottom, a large number on top divided by a small number gives you a large number, and vice versa. Small number on top, larger number on the bottom will give you that smaller number as well. Now, we also talked about a way to go between those two K values, the Kp and the Kc, depending on the information given to you in the problem. If you're given atmospheres or pressures, you probably want to calculate the Kp value first. If you're given some type of concentrations, then you would probably want to calculate something like Kc first. But you could use that equation that the Kp equals the Kc times RT to the delta N. Again, R being the gas constant, and that's the one with energy, the 8 point, no, it's not the one with energy, I'm sorry. It's the one we use in the ideal gas law, the 0.08206. The temperature does need to be in Kelvin. And the delta N, as we talked about, is the change in the number of moles of gases that you see in the equation. So it's just the gases, and we do products minus reactants when we calculate delta N. And again, that's important because if you do get the negative when you do that, you don't want to sort of ignore it, because mathematically speaking, if you ignore the negative, you will do the wrong math, obviously, when you do the calculation. So that's a nice way that you can go back and forth. Generally speaking, when we talk about sort of pressures and Kp and all that, definitely when we get into sort of ice tables here and not too long of a time, you definitely want to make sure that the pressures are in atmospheres. That's usually your standard unit. So if they are in something else like torr or millimeters of mercury, pascals, whatever it may be, when we get into sort of ice tables, you want to make sure that they are in atmospheres. And that goes with even if the question sort of gives you pressures in torr or something like that, and they're like, what is the pressure in torr? When you do sort of the calculation part, you do want to make sure that they are converted to atmospheres and then go and convert them at the end. Yeah, so again, Kp would deal with obviously just gases, right? So P is really pressure. So if you had an equilibrium that did not have any gases involved, you would not have any type of Kp or any value like that. So it does definitely has to have some gases in there. So I think we saw one, we saw a couple, but we saw one where it was all gases, obviously. And then we saw one, I think that was like a gas and a solid type of situation. So you do need some type of gas to have a Kp sort of interaction. And then lastly, I think what we finished up talking about was there are some different ways that you can manipulate K values. And sometimes you need to do that because you're asked what is the K value of a overall reaction. And maybe you're given individual reactions that you're are given in a problem, and each of those have a K value associated with it. So there's several different ways that we can kind of manipulate an equation. But the first important thing, as we talked about as well, is that when you do see a K value written for a particular reaction, it is based on the actual reaction, exactly how it's written, and for that particular temperature. So another thing that we sort of touched upon last time was that the value of K is only affected by when you change the temperature. So if you keep the temperature sort of constant at a, say, 25 degrees for an entire set of experiments, the K value that you should calculate for that should be the same all the way through. Again, regardless of how much starting material you start with. But if you took it from 25 degrees to 50 degrees Celsius and did the same experiment, the K value would change between 25 degrees Celsius and 50 degrees Celsius. But if you then kept it at 50 degrees for a bunch of experiments at that point, it should maintain the K value at 50 degrees for all those experiments as well. So sometimes we do need to manipulate these equations or reactions to do that. You wouldn't necessarily have to account for it in the equilibrium expression for a temperature change. What essentially would happen is, for example, trying to think here, we don't do it at this school, but another school I teach, they would do kind of like the experiment we're going into, experiment 2 and experiment 3, but they would do it at room temperature, for example, and they did a whole bunch of trials at room temperature and how to calculate the equilibrium constant for it. And what you should see is at that first temperature, they all should be about the same. And then what you would do is basically the same experiment, but throw them into like a boiling water bath and kind of raise the temperature. And then you would do the exact same experiment with the exact same starting amounts that you did at the lower temperature. But what you would see is the equilibrium constant would change as well. So in terms of the actual expression for K, it won't affect it, but it will affect sort of what will happen to the value of K. And that's also dependent on what type of reaction it is, if it's exothermic or endothermic, which we'll talk about a little bit towards the end of this chapter as well. But regardless of the temperature, the K expression will still be the same. It's still the concentration of products over reactants, with the appropriate coefficients. So when we do manipulate these equations, the couple of common things that we have to do is add a couple of equations together. When we add two reactions together, again, things on opposite sides of the arrow that are the same will either cancel or reduce down. But when we add two sort of equations together, what we do with the K values for each of those is we multiply them together. And that will give us the K value for the overall reaction that we did. If we need to reverse a reaction, essentially when we reverse a reaction, what we're doing is making our reactants our products, or products our reactants. So what that does to the K value, as we talked about at the very end last time, is we typically take 1 over the K value when we do that. And the other two things that you commonly could do is you may have to multiply an equation by a common number. And if you multiply, say, by 2, what you would do to the K values, you would square it. If you multiply, say, by 3, all the way across an equation, you would like cube the K value and so forth. So whatever common number you multiply the equation by, you take the K value to that sort of exponent, if you will. And the last thing that you could do is you might have to divide a bunch of equation or an equation by a common number. And if you divide by a common number, what you do is take the root of that K value. So if you divide it by 2, you would take the square root of the K value for that equation. If you divide it by 3, you take the cube root and so forth. So these are, again, ways that you can manipulate individual K values for reactions. And in a case where you need to kind of use multiple equations to sort of build an overall reaction. That was a lot. Now I'm tired and I need a nap. But any questions on what we talked about last time? Okay. So I think this is about where we left off here in terms of our lecture. So it probably summarizes what we just talked about, but I was just going to go through it real quick. Again, the concentrations when we deal with sort of equilibrium constants or just equilibrium calculations, usually concentrations should be molarity. As I mentioned earlier, if you have something that deals with pressure, probably good practice to get them into atmospheres, as that's usually the standard unit of pressure. And again, even in a question where they may say, give it to me in another unit, and they give it to you in torr or something like that, you still need to do that. Again, as we talked about, solids, liquids, we don't include in our equilibrium expression, which usually means we're going to leave out things like water, which is sort of the common pure liquid that we come across. No units associated with it. And as I mentioned, as we went through it here, again, the equilibrium constant is specific for the reaction, the way it's written, and also at that particular temperature. And then the couple of ways to manipulate that we just talked about. And I think this is also what we were just talking about as well. Again, multiplying by a common number or dividing by a common number as well. All right, so again, the key thing to take home, and like I said, sometimes people have a lot of confusion sort of on that part of it, is what we see here. You know, like I said last time, I think people oftentimes think like, how could that be, again, if we sort of start with different amounts in these reactions, when it reaches equilibrium, how could that value still be the same? And it ends up being the same regardless really of where you start with in terms of even reactants, products. You know, you can start with some reactants, some products, whatever it may be. but it will always, in terms of the ratio of the products to the reactants, it will pretty much always end up at the same sort of ratio there, regardless of how much you start with in each, say, trial or whatever you do. Again, the only thing that will really affect it, the actual value of it, is if you change the temperature. And that's sort of a comparison from one temperature to the next. So again, as we talked about. All right. So then let's talk about another letter here, and for a nice change of pace really quick. And this is Q, and Q is what is referred to as the reaction quotient. And Q is basically calculated the exact same way as how you would calculate the equilibrium constant. So if we were going to calculate Q, Q would still be our products divided by our reactants. So it's exactly the same deal as what you do with K, all the way down to the point where you would still use the coefficients as those exponents and everything just like you normally would do with K. Now, the difference between sort of Q and K is we use Q really in sort of two different situations. It will come about. One situation is just a straight out sort of Q question, if you will. And that question is, are you at equilibrium, is what we kind of can use Q to help us determine. And that's in a situation where we're given basically sort of the initial concentrations of everybody. The initial concentrations of everybody are, we have the concentrations of everybody that's there, but we're not sure if we're at equilibrium or not. Obviously, in order to calculate Q, you need the concentrations of everybody in the reaction. So if you're given that, that's a pretty big hint that you probably should calculate Q at some point, if you're going to do some type of calculation like that. So again, you would do your products over your reactants, just like you would do with your K. And when we would calculate Q, we could compare it to the K value for that particular reaction. And as we see here, if the Q is greater than the K value, the first thing that tells you is this reaction is not at equilibrium. And in order for it to reach equilibrium, it pretty much needs to go to the left, sort of opposite of where it's pointing. So it needs to go in that direction towards the reactants. So in order for it to reach equilibrium, you would need to start making some more reactants. And when you do, then obviously it can get to equilibrium. If you calculate Q and it's less than Kc, it also tells you it's not at equilibrium. And again, opposite of where it's pointing to, this would tell you that you need to make more products. And if you calculate Q and it actually does equal the K value, that tells you that you are at equilibrium and the system is out there. Yeah, so for using Q, so sometimes people later on try to determine, should I do Q or not? So for example, if we had just a reaction such as this, like A plus B, right, goes to C, right? We would do Q would be the concentration of C divided by A times B squared. So again, just exactly how you would do it if you were doing K, exact same deal. It's pretty much the identical deal. Now, in order to obviously calculate Q and actually get a number, that would imply that you would have to be given everybody's numbers at some point. Like they would have to tell you, hey, you started with 5 molar A, 2 molar B, and 3 molar C. Obviously, in a situation, if they just tell you you started with 2 molar of A and 3 molar of B and nothing about C, you have no way to calculate it, right? So the big sort of hint that, especially with ICE tables, or if it's not a straight sort of Q question, is that if you're given the starting amounts pretty much of everybody and you have the ability to calculate Q, you would want to do that. Hang on, I'm just trying to read what's going on there. Yeah, it can be the same value, obviously, as you can see here. It is possible if Q does equal K, then the system's actually at equilibrium at that point. So that's essentially what that would mean at that point, is that it is at equilibrium. So they can't equal each other. And it means basically the center thing here, right here, that that system is at equilibrium. It's only when they don't equal each other that that system is not at equilibrium. Yeah, so you do it the exact same way as K, which means just like the equilibrium expression, you would not include anything that's solid or liquids with Q as well. So for lack of a better word, it's pretty much K, which is just a different letter. Yeah. So you do everything the exact same thing, but really the main purpose of Q is to figure out whether or not you are at equilibrium. So when you're given, for example, the starting amounts of everybody in a reaction, you know, that would imply that obviously that reaction perhaps has already started. It's already going because you got some reactants, you got some products going there. So you could use Q really to determine whether or not you've already reached that point of equilibrium. And if not, which way you kind of have to go to get there. So just to reiterate, two places where Q will really come into play. And like I said before, there's just a straight out question that's like a Q question, and it's a straight out question of, hey, you're starting with all these guys, this amount of everybody. Is this system at equilibrium? And if it's not at equilibrium, which way it needs to go? So that's probably 9 times out of 10 where you're going to use Q is in a question like that, where it's just straight out, hey, are we at equilibrium or not? The second place where we typically will use Q is when we actually do like calculations with ice tables and figuring out equilibrium concentrations, because it can help us determine whether or not something is obviously at equilibrium or not, but more importantly, it will help us give us a direction as to which way the reaction needs to go to get to equilibrium. So we'll come back to Q a little bit later on after we sort of talk about it in more of a, what we're going to talk about now is sort of just a straight up Q type question, but we'll see where it'll come into play a little bit later on when we do ice tables and do some of those calculations as well. All right, so let us actually do an example here. So why don't you take a minute or two and work through this example here. We want to know, is this system at equilibrium? And if it's not, which way does it need to go to reach equilibrium? So take a minute or two and start working through it, and then we'll kind of talk about it. Okay, so let us take a look here. So again, we want to calculate Q, and to sort of answer a question I think I see there. Um, yeah, so K does describe the equilibrium. Q, as you kind of say there, does describe sort of a point in time of where you're at. And that point in time may be a point where you are not at equilibrium, but it also may be a point where you actually are at equilibrium as well. So again, obviously, if Q equals K, it would be equilibrium at that point. And they both would sort of be the same in that sense. But at that point, it could obviously not be at equilibrium, which then would either be Q would be less or greater than K. So to do our Q here, again, we would set it up exactly like K. So we're going to take the concentration of NH3, and we do need to square it. We're going to divide it by our reactants, which is N2, and our H2. And again, here we do want to make sure that we do cube it because of the coefficients there. In this particular case, we have moles and we have liters, so we do want to convert everybody into molarity, which is moles per liter. So that's probably the first thing that we want to do here. And if we did that, I think I got it going on here. So it looks like if we converted everybody into moles, which again, a molarity, which is taking moles divided by liters, looks like we get 0.0711 for our N2. We get our 0.00917 for our H2 and 0.00183 for our NH3. So really what we need to do is just kind of plug it into that expression that we had earlier. And if we do that, it looks like we do get a Q value of 0.611. Now, when we do that, what we now want to do is take that Q value and basically compare it to the K value that was given to us. And if we look in the problem there, because I'm old and I don't remember, it's 1.2 is the K value there. And that means that in this particular case, Q is less than the K value. So the first thing that tells you is this system is not at equilibrium with this starting amounts of everybody that's here. And the second thing that it tells us is since Q is less than the K value, it needs to go towards the product side to reach equilibrium. And I would say this is a very typical Q type problem where this is sort of the question, are you at equilibrium and which way you need to go? Any questions on that calculation there? All right. So let's talk a little bit about actually solving equilibrium problems. And remember that obviously if you want to get the equilibrium constant value, you do need to obviously have the equilibrium concentrations of everybody. But if we are given just the initial concentrations, then you have to do sort of a calculation to determine the equilibrium values. And the way that we commonly do that is through the use of what are known as ice tables. And ice tables, I is initial, C is change, and E is equilibrium. So we use these ice tables to calculate the equilibrium concentrations of everybody when we're given basically the starting amounts or the initial amounts, or if we're just given information about maybe the reactants and not the products and so forth. So you might be familiar with ice tables. They do teach it at the very, very end of Chem 3. I don't know why they do it so early, but they do it way at the end of Chem 3. And sometimes people use ice tables to do limiting reagent type problems, stoichiometry. So if you sort of done that approach, you know, it's kind of a similar sort of thing. But ice tables is pretty much the big calculation here for the entire semester. And we do use these to basically determine the equilibrium concentrations. So when we do this, and when you do any type of math, obviously you only want sort of one unknown, right? It makes it a lot easier to sort of solve for. So in ice tables, we typically will use X to represent the unknown, and X is really what represents the change part of the ice table. So X here is usually used to represent that change part. And what we can do is we essentially will solve for X. And when we solve for X, that will allow us to get the change and then allow us to get everybody's equilibrium concentrations. So just to kind of show here, kind of a fake example, if you will. So let's say we had, I'll do it up here. Let's say we had this equation. And let's say initially we were told that we started with an initial concentration of 2 molar for A, an initial concentration of 4 molar for B, whatever it may be. So initially what we would do is we put into our table 2 and 4. And if you're not given any information about your products, it's probably safe to assume that you're starting with 0 for your product side. So a lot of problems, they won't give you any information about sort of the product side. They'll just give you some information about the reactant side. And it's safe to assume that you're initially starting with 0 on the product side. Now, this is where the change part comes into play. Now, if we are definitely not given any information about the products, it is probably safe to assume that this reaction is proceeding from reactants to products, so in this direction, right? That also should mean that we know that the concentration of our reactants should start to decrease with time, while the concentration of our products should start to increase with time as we start to make products. And that's important for our X part in terms of minuses and pluses. So since we're assuming the reaction is heading towards the product side, we're going to assume on the reactant side, those guys are going to be minus X's. That way we're going to decrease some of their concentration. While on the product side, we would assume that it would be positive X, as it should be increasing concentrations as you get over there. The other really important thing when you get to the change part is everybody's favorite thing in chemistry, right, is stoichiometry, right? Mole to mole relationship, blah, 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 right? All that good stuff. So in order to get the correct mole to mole relationship when you do these sort of ice tables, you actually do have to take the coefficients into account in your ice tables. So this would be minus 2x when we do it. The 2 comes from the coefficient there. And really what that's going to do for you is all the mole to mole relationship for you when you're kind of doing this reaction or this calculation. Same thing here. When we get the B, it also has a 2. So this would be 2x for B minus 2x. Now, when we get to the product side, again, we should be assuming that it's increasing. So this should be plus 4x over here in my really badly made up numbers. And that would represent the change part of the ice table. And what would happen is we would come down to equilibrium, which I'm going to write underneath here as I think I'm getting out of room, bad choice. And that would take us 2 minus 2x for our first one. It would also give us 4 minus 2x for our next one. Since I got some room up here, I'll just go 4x right there. on my screen that's above everybody's picture. So I don't have a lot of room there. So we would carry down everything really to the equilibrium line. So this is essentially what an ice table looks like. And the goal here is really mathematically, we need to solve for X. So how do we solve for X? We're actually going to use our, so I'm going to explain how to solve for X right now, if that's what you're asking. But if you're asking how we got the 2X and 2X and 4X in the table, if that's your question, the 2, and the 4 come straight up from the coefficient in the balance equation. So there's nothing, you know, it's kind of just like the mole-to-mole relationship you would do in stoichiometry. And that's where the 2, and the 4 comes from for the X. And again, that's really important to do. That way you do get the right mole-to-mole relationship when you do it. So it comes just from the balanced equation and the coefficients, okay? And that's why it's also really important to make sure your equation is balanced, although I'll be honest with you, in this part of the class, they're usually balanced, but you should check just to make sure. But, you know, they usually are pretty balanced. But if not, you want to make sure it's balanced, again, so you get the right mole-to-mole relationship. So once you sort of get that ice table sort of together, the goal here really is to figure out what X is. And the way you could do that is we could write our equilibrium expression for this guy, which would be the K is equal to C to the 4th divided by A squared times B squared. And let's just say, for example, the other piece of information they would give you in the problem is, hey, K equals 125. Just made up the number right now. And you would know that this sort of ratio equals 125. And what you essentially would do at this point is take all your values that you have for the equilibrium line and put it into this expression. So you would have 4x, and in this really bad example here, you would have to take it to the 4th. And you would have A, which is 2 minus 2x, and you would have to square it. And you would have B, which is 4 minus 2x, and also has to square it. And that equals 125, yeah? So this is really where the math part of it comes into play. That looks super scary there, what's going on in that equation, right? But we probably won't have something that difficult, but there's a few different ways mathematically that we will solve for X. One, probably the hardest way we'll get into in this class is the quadratic formula. So you could use something like the quadratic formula, which is, you know, just a reminder. I'm talking to myself, really, a reminder, because it's been a while. But I think if I remember correctly, the quadratic formula or something like that is like X is equal to minus B plus or minus the square root B squared minus 4 times AC divided by 2A. And that's based off of AX squared plus BX plus C equals 0 type of formula. And that's probably the most complicated way that we'll get into it. Sometimes you may not have to always use the quadratic formula. You can maybe find some other ways to solve it, maybe some perfect squares or something like that that you could do. So there's a few different ways you could do it. But probably the most complicated way will be something like the quadratic formula. So in this example here, obviously, it's a little bit more complicated one than what we got going on. So I'm just going to pretend I solved it mathematically. Good for me. I did great math there. And my math came to tell me that it was like X equals 0.01 or something like that. And again, that is definitely probably not the right answer, I'm sure. But what that does, after you would solve it mathematically and solve for X, the importance of that is when you go back to the equilibrium line, you then would have the X value that you need to actually get the individual values of everybody at equilibrium. So that's essentially sort of the procedure that you want to follow when you do an ICE table calculation. We use the equilibrium expression, we use the value of K that's given to us, and we solve for X. And we're going to do several examples here through the next couple of slides or so of some different types of calculations, sort of different ways that you can sort of solve for X and so forth. The quadratic formula, as you know, does give you 2 values of X, right, when you do solve for it. And you will always have usually one value of X that does not make sense. So let's just talk about what would not make sense in a situation like that. If you got a value of x, for example, and let's just say x equaled 4 in this made up example, when we solved for it, as one of our values we would get for the quadratic. When I would put the 4 back into this first one here, right, that would give me 2 minus 2 times 4, which is 2 minus 8. That's like -6, right? And -6 is not so good because you shouldn't have a negative concentration, right? So one of the values when you use quadratic formula, for example, will lead you to a negative concentration or something like that, or even a negative pressure. And that obviously would not be the correct value. And you then could use the other value, which should hopefully give you a positive value. So you will definitely get kind of like two values when you use the quadratic, and one of them won't make sense. But in terms of answers that you get for the quadratic, just sort of a preview, it is possible to get two positive numbers, right, in the quadratic when you solve for it. Could get two negative numbers, could get a positive and a negative number. So there's all different combinations in terms of x's that you could sort of get when you solve a quadratic formula. But there will always be, regardless of if they're both positive, they're both negative, one's positive, one's negative, when you do put it back into that equilibrium line, one of them will lead you to a negative concentration. All right, so why don't we go through one here just to make sure, so to see, I think we got one. All right. So the equilibrium constant for this reaction is 7, and the initial concentration of Br2 is 0.663. We want to calculate the equilibrium species for each of these. So we'll go through this together again just to kind of show you the points of it here and make sure everybody's on the same page. So again, we would start with our reaction here. It is balanced, so that's good. And in this particular case, we're just given the initial concentration of Br2 and nothing on the Br side. So initially, we could go that this is 0.663. And since we were not given anything on the other side, we can safely assume that this is going to be 0 to begin with. Now, when we do our change part, because we weren't given, again, anything on the product side, just like before, it is probably safe to assume that you could roll this way. And when we do go that way, again, what that means is our reactants should start to decrease with time, which means on the reactant side, it should be negative, while our products should increase with time, which means they should be positive. And again, this is where we're going to use x to represent our change. So this would be minus x. The coefficient here is 1. This would be plus 2x. And again, the 2 comes from the coefficient that we got going on there. Now, when we get to equilibrium, we're going to drop all that down. So 0.663 minus x and 2x. Any question on sort of the ICE table or how we got through the setup of it? Okay, so now a couple of things that we need to do, obviously, at this point is we need to solve for x. So we do want to use our equilibrium expression. So in this case, K would equal the concentration of Br. And we do need to square it, again, because of the coefficient that we see here, divided by Br2. And that's going to equal 7 in this case, as that was given to us in the reaction or the formula. What we're going to now do is take everybody on our equilibrium line, and we're going to put it into that expression. So that would give us 2x, and we do need to square it on top, divided by 0.663 minus x on the bottom. And that is going to equal 7. Yeah. So now we need to do some math here, right, to calculate x. So we need to multiply the bottom part to the other side. And we also need to obviously square the top part. So if we square the top part, that's going to give us 4x squared. And if we multiply the 0.663 minus x to the other side, we will get a number, maybe. Oh, there we go. We will get 4.641 minus 7x. Yeah. And again, all I did is multiply the bottom to the other side. And now what we want to do is combine everybody to the same side. So if we do that, that will give me 4x squared plus 7x minus 4.641 equals 0. And that's in the form of really the quadratic, right? So this right here is our A. This is our B. And this is our C, right, from the quadratic. So we do want to solve it that way. So why don't you take a minute or so here and see what you come up with. I'll do it as well. Make sure everybody gets the same answer. And again, a reminder, the quadratic is x is equal to a minus b plus or minus the square root of b squared minus 4ac divided by 2a. The initial numbers for the ice table came from the actual problem right here. Okay, so let's see how we're doing. So we put our numbers in. We got x is equal to minus b, which would be minus 7, plus or minus. Now, if you do everything in the square root part, looks like you get something like 123.256. And then if you take the square root of it, you get something like 11.10 when you do that. And you're going to divide that by 2 times a, which is basically 8. And if you do that again, you're going to do this 2 ways, right? We're going to do positive first. So minus 7 plus 11.10 divided by 8 gives us 0.513. Or for our second one, we're going to do minus 7 minus 11.10 divided by 8 gives us minus 2.26. Any questions on that? And again, yes, so to answer your question, because we weren't given anything about the initial concentration of the products, it's safe to assume that you're starting with 0. Now, when we get these two numbers, these are our x values that we could put back into our equilibrium line there to figure out our value. And right off the bat, we should see that for our BR, it's 2 times x, which means if we take that minus 2.26 and put it back in there, that's going to give us like minus 8-ish or so. And that can't happen. So we can eliminate this value here because that's going to give us a negative concentration, which means our correct value here probably should be our 0.513. And that is not good. Let's do that. So we're going to now take our 0.513 and put it back in, which means at equilibrium, BR2 would equal 0.663 minus 0.513. And that's going to give us, what we got there? 0.150. And it is molarity, right? Since we are doing a concentration. And this is BR would equal 2 times X, which would be 2 times 0.513. And if we do that, 2 times 0.513 gives us 1.03, we'll call it, as our equilibrium concentration of each of those guys. Any questions on where we got those numbers? Now, the other good thing about math is usually in math, you could kind of check yourself and make sure you didn't, screw up per se. And because now that we have the equilibrium concentrations of everybody, we should be able to, if you have time, and it's a good idea to do sometimes, so the math is a little crazy sometimes on some of these, we could actually go back into our equilibrium expression here. So we can now take our equilibrium values back in. So take our our 1.03 squared divided by our 0.150, and we should get about 7. And if you do that, you do get about 7, give or take with some rounding, but you do get pretty close to what the equilibrium constant is. So the nice thing is you could actually kind of check yourself if you have the time. And I would recommend doing that, especially when we get into a little bit more complicated ones involving the quadratic, where there's a lot of factoring and all kinds of stuff that you have to do. There's a lot of places where people can kind of mess up on the calculation part. So the nice thing is you could kind of check yourself to make sure you're at least in the right ballpark. You didn't screw up too much, I suppose. Yeah. Any questions on that? All right, so why don't you try one here? I think we got another one coming up. Hopefully that's what this says here. That's good underneath it. All right, there we go. In case you want to see it nicely written, unlike my bad scribble there, you could watch this back later and see it nicely done. All right. All right, so why don't you give this one a go here? We're looking for the equilibrium concentrations of everybody we got going on in this one. So see what you come up with, take a couple of minutes or a few minutes and start it, and then we'll get going on it together. Just same page. It could actually be either one. I'm not sure exactly which one it is because remember you could do it by concentration as well. Just because they're gases, you could figure out the concentration. So it could be a Kp or Kc in this case. But you could potentially have a Kc or Kp in this case. Truthfully, I'm not sure exactly which one this one is, but it could technically be either one. My guess is probably the Kc. All right, so let us kind of see how we're doing here. And let me get a kind of a fresh place to write, maybe. All right, let's give it the old college try here. Move that over there. All right, so we have, I think it was H2 plus some I2, giving you 2HI, I believe. And in this particular case, we were starting with 0.5 moles of H2 and 0.5 moles of I2, and they're placed in a 1 liter flask. So that means that essentially the concentration of H2 would be 0.5 moles per 1 liter. It's going to be 0.5 molar. And our I2 would be the exact same here. It's going to be 0.5 moles over 1 liter and giving us 0.5 molar. So our initial amounts here, again, are going to be 0.5 molar. And you do want to convert it into molarity before you go into the ice table. So that's going to be our initials. 0.5, 0.5. And again, we weren't given any information about the HI. So it's again safe to assume that we are starting with 0 there for that guy. Now, our change part is going to be minus x, and plus 2x, again, for our 2 that's there in our balanced equation. And again, since we are assuming that this reaction is proceeding in this direction, that's why our minuses are over here on our left and our pluses on our right, which means at equilibrium here, we end up with 0.5 minus x, 0.5 minus x, and 2x. Any questions on the ice table setup there? Again, here we do need the equilibrium expression. So K would be our HI squared divided by our H2 and our I2. And that equals, that was 54.3, I think, on the other slide. And again, if you do have questions, feel free to ask them in the chat there. Now, just like we talked about before, we're going to take our equilibrium, guys, and put it into that expression. And that's going to give us 2x squared divided by 0.5 minus x times 0.5 minus x. And that's going to equal 54.3 in this case, yeah? So now we want to solve it, and we always want to solve things perhaps the easiest way, right? So hopefully you recognized it, but if you did not recognize it, you could put like a big square root on both sides because this is like a perfect square on both sides. Or you could just go down that path of quadraticness if you like that even better, but you could square this side, square root this side. And if we square root the left-hand side, we get 2x. We're left with a 0.5 minus x. And the thing I always forget to do, and most people, take the square root of the other side, not just write 54.3 again. So 54.3 is like 7.369. So at this point, it makes them a little bit easier to solve since we could do that perfect square. If you want to go through the longer route, you should hopefully get to the same idea or place. We're going to multiply that to the other side. So that's going to give us 2x equals something. Let's see, times 0.5 gets us 3.684 minus 7.369x. I'm going to combine my x's by bringing the 7 to the other side, basically. That's going to give me 9.369x equals 3.684. We're going to divide the 9.369 to the other side, and we will end up with an answer, maybe. We'll end up with an answer of x. I hope we end up with an answer, right? 393 would be our x value in this particular case. Any questions on that math? So again, a reminder, you don't always have to do the quadratic, right? You know, there are some other ways that you may be able to do it. And I recommend going the easier route because less chance of error that way. But again, if you kind of go the full out version there, you should still hopefully end up with the same answer at the end. Now we are not really done. We now need to take that 0.393 number, and that really is just our x value or our change that's occurring here. So we do need to go back and put it into our equilibrium line, which means our H2 would actually equal our I2 in this case, and that would give us 0.5 minus 2 times x, right? Not 2 times x, wrong guy. It would just give us 0.393, just minus x, and that would get us 0.107 for each of those. And again, it is a concentration, so you do want to lay up the molarity there at the end. And for our HI, that is the one with the 2. It's going to equal 2x, so that would give us 2 times 0.393. And we will end up with 0.786 molar. And those would represent the equilibrium concentrations of each of those guys. And just like previously, you can check yourself if you like. You can put those values back into the equilibrium expression. So we would take 0.786 and square it. and divide it by 0.107 twice. And we end up with 53.96, which is about 54. And again, we're good in terms of that. Any questions on any part of that? I see your question. We're actually going to get to that in an example in just a second or two, or another example. But there is something to do when we have a K value that's on the relatively small side versus the large side. Other questions on that? So we were talking about Q as well. So this is a good point to sort of talk about Q just for a second. This is a place where Q could come into place. Just fix that there. I'm back. All right. That we should a place where Q could come into place. And that's a situation where you're given the starting amounts of everybody, and it will help you determine, you know, which way the reaction is going. And it would really affect the change part of it. So sometimes you do need to use Q to kind of help you out with that change part and determine which way it's going. Probably 9 times out of 10, minus is on the reactant side, plus is on the product side is probably the way it's going, but is another place where you can use Q. Any questions on this particular one here? All right, so let's continue rolling through. So let's try this one again, but now we have a few different concentrations here. So take a little bit of time here and see what you come up with on this particular one. Again, using the same value of K and also the same equation. So give it a go, see what you come up with. I'm going to give it a go as well. There's a lot of fun math in this one. Okay, since we are getting towards the end here, let's do a couple of things, I think. Let's start talking about this one, and you probably need some more time to finish it. So you could finish it tonight, and then we'll go over it starting tomorrow during lecture. But let's just kind of look at this one. It sort of touches upon that point I was making just a second ago. In this particular one, we're doing the same reaction, and we're starting with 0.00623 molar, 0.00414, and 0.0224. In this particular example here, we're looking for the equilibrium concentrations, but we're given the starting amounts of everybody that's there. So this is the second sort of place where Q should be calculated. And the reason, again, you should really calculate Q in this situation is you're not really sure if it's at equilibrium. And my guess is it would not be at equilibrium. Otherwise, it's not much of a question. But more importantly, what it will tell you is which way it needs to go to reach equilibrium. Do you need to go to the product side? Do you need to go to the reaction side? And that's what's going to affect the change part of that ice table, like I was talking about. So if we figure out that it does need to go to the product side, the change part should again be the minuses on the reactant side, pluses on the product side. If we happen to find it goes the other way, then you would want to reverse those things, right? The pluses on the reactant side and the minuses on the product side. So really the first thing you should do in this type of problem, because you are given everything, is calculate Q. And a reminder that Q is calculated the exact same way as K. And we're just going to put in the concentrations of what they gave us. So this is our products over reactants. Putting in our concentrations here, we see that Q in this case is 19.5. And if you remember, the K value here is 54.3. So it tells us it's not at equilibrium, which we could probably guess because, again, it wouldn't be much of a question at this point. But more importantly, what it tells us is it does need to proceed to the product side to reach equilibrium. So what that means, again, when we get to our ice table part, we would hopefully have something to write with. There we go. When we get to our ice table part, we could safely feel good about doing minuses on this side and pluses on this side as the reaction is, again, proceeding in that direction. Well, the purpose of doing Q right now is to further convince yourself that this reaction is heading towards the product side. We actually haven't done the problem itself. This is just to confirm the fact that this reaction is proceeding from reactants to products, as opposed to if we found the other way, it would tell us it needs to go this way, right? If we found Q was greater than. And again, what that would affect is the change part here in terms of the minuses and the pluses. But you really should do Q here before you actually get to the problem, just to verify which way that reaction is going. Again, I would say in reality, probably 9 times out of 10, even if you blew right by this part and just went right to the problem, you'll probably be okay. But in reality, you should really check it just to make sure. Other questions on that? So since this one's a little bit longer, as I'm hoping you're finding out right now, again, you should continue to work on it and hopefully complete it. And we'll talk about what the answer is at the very beginning of lecture tomorrow. Yeah. Any questions on that? So we'll officially kind of stop lecture here for now. Got into some good ice tables and stuff. And believe it or not, we're pretty close to finishing the first chapter. So that's pretty good. Today we are doing experiment number 2. So there will be a video we'll kind of go through together. There'll be some calculations that you need to do and everything like that. So make sure obviously you have the paper and stuff like that. You'll need to upload it at some point, and we're going to kind of go through the videos. Hopefully it'll work out okay kind of together. We're going to kind of stop the video. You'll get some opportunity and some time to do some of the calculations. We'll kind of pick up the video and all that kind of stuff. So we'll start lab so everybody can get up and stretch a little bit. How about we start lab about 3:10, and that way we can kind of get up and stretch and move around a little bit before we sit for another 3 hours or whatever it is. All right. So if you're all good, if you didn't write here for roll, please do so now before you take off. And I'll see everybody about 3:10 for lab experiment number 2, I believe it is. Okay. All right.